Nexi is a green construction and technology company. We design and manufacture high-performance buildings and green building products that are sustainable, cost-efficient, and resilient in the face of climate change. Our mission is to build a vibrant future for people and the planet. Next slide. Because each new plant involves a heavy capital investment, our growth strategy is based on a licensing model, not unlike Coke and Pepsi. We find developers and partners with great track records in their markets. To build our plants, we provide complete turnkey equipment, training support, sales and marketing support, and continual innovation and engineering, and providing them the proprietary materials, which for us is our Nexite, which is our polymer concrete. We currently have 3 plants operational, a 20,000 square foot plant in Moose Jaw, Saskatchewan, which was the original one. We have an 85,000 square foot plant in Squamish, and we recently opened a 125,000 square foot plant in Hazleton, Pennsylvania. As you can see, we are concentrating currently on North America, and eventually we'll move to markets abroad. And with that, I'm going to pass it over to Zosia, who will run you through the next several slides.
Hi, good morning, everyone from the West Coast, and thanks to Laurenz for the intro and Brandon as well. I'm going to provide some context around global mega challenges that we're facing and how Nexi is aligning our solution to meet these challenges. So first and foremost, climate change is upon us. We're living in a climate emergency, and natural disasters will continue to intensify, as you can see in the bar chart here from the United States. 2020 broke all previous records from the last 40 years, and here in British Columbia, we experienced record-breaking heat waves as well as catastrophic flooding this year within a span of 6 months. So, and buildings and construction are a key part of both the climate crisis, but also climate solutions. We know that our industry represents 39% of global CO2 emissions, and that comes down to how we heat and cool our building. It's from construction-related emissions, waste from demolition, emissions tied up in the materials we select as well. That number's been ticking up by 1% per year since 2010 and will continue to increase because we're building new buildings at an incredible rate. The volume of buildings on Earth is expected to double in the next 40 years. That means that it's absolutely critical that we design new buildings right, but also 100% of the buildings on the planet today are existing buildings. So we need solutions that can scale for both new and existing buildings to help us on the net zero pathway. Materials are a huge contributor to this challenge. Cement in particular is a large emitter of global CO2, representing it's the 3rd largest emitter in the world if it represented a country. Steel as well, and this is important because the building sector is considered a market pull for materials. We consume up to 90% of concrete globally and 50% of steel. There is a lot of pressure on these industries to innovate themselves, but it's also on us as a building industry to create innovative designs that favor low carbon materials. And then, of course, we have a huge waste problem. Why do we have waste associated with construction? Well, the design life cycle of our buildings is incredibly short. And the wasteful nature of on-site assembly is a big part of it as well. And we continue to demolish at the end of life. We've got some deconstruction efforts starting to mobilize, and the policy landscape is shifting to mandate construction waste recycling and reuse of materials, but that still represents only 1% of building end-of-life scenarios. And so we need to be thinking about both operational carbon and embodied carbon aspects of the built environment. Operational carbon meaning the emissions tied up with how we heat, cool, light our buildings and generally keep them running. And the embodied carbon portion of it is emissions associated with extracting materials, manufacturing building products, transporting that all to the construction site, assembling buildings, and the end-of-life emissions as well. We used to think that embodied carbon, which was a much smaller piece of the puzzle, But that is starting to change. And this graph here by the Carbon Leadership Forum shows where the key impacts are from embodied carbon. First and foremost, it's right up front when we produce building materials and construct our buildings. And then you have a couple more hits during the building life from renovation and maintenance. But what you see in the blue is whether the building is a standard performing building or a high performing building, operational carbon emissions are trending downwards. And that's because A, our buildings are getting more energy efficient by code, and B, the grid, the energy grid, is gradually getting cleaner. So that means that embodied carbon emissions are going to take a much greater role as we evolve here. And AIA, the Architecture 2030 estimates embodied carbon will represent 50% of building-related emissions by 2050. So that's just an overview of a number of global mega challenges we're facing and how Nexi is specifically aligning ourselves to meet multiple of these challenges at the same time. So where do we need to be by 2050? Well, science tells us that if we want to hold off on some of the worst climate impacts, we need to reduce our global temperature rise or limit it to 1.5 degrees C above pre-industrial levels. And to do that, there's two numbers to bear in mind. One is half current emissions by 2030, and two is net zero emissions by 2050. What we can see from this graph from the IEA that just came out last spring is that our window is incredibly narrow. It is this decade that we need to really shift and decarbonize all sectors of the economy to get on this net zero pathway. So we're talking about massive deployment of all available clean tech within the next 9 years and tripling the speed of efficiency progress. Buildings are a key part of that. And the good news is that we know that near-term emissions reductions really do work. In other words, every ton of GHG that we avoid really does slow down global warming. So for buildings, it's about energy efficiency. It's about reducing demand first. It's about electrification, providing that energy from electricity and clean, renewable electricity. And if we can generate that on building rooftops, even better. And there's a big piece around behavioral change as well, how we consume energy in our buildings, but also the behavior of designers and the building industry in selecting and designing to support low carbon materials. So in summary, how do we get there by 2030 or 2050? Really thinking about low embodied carbon materials, zero emitting new construction and renovation. So we want all new buildings to be zero carbon ready by 2030, and the vast majority of existing buildings to be zero carbon retrofitted by 2040. We've talked about electrification, renewable energy, getting a better balance between smart and occupant control, and then really designing for more extreme weather events and an increased range of environmental conditions, as well as design for durability, disassembly, and reuse. Thinking really hard about embodied carbon in buildings and whether demolition is necessary. The good news is that momentum is building to support this net zero carbon transition in our sector. We know that thanks to the creativity of the design and construction community, we know that we can achieve zero emission buildings in any climate worldwide now. And so we're seeing a real alignment around the standards landscape here, whether it's CAGBC or the USGBC or the Living Future Institute, BREEAM and others are all really aligning around this zero target, zero carbon, zero energy, and zero emissions. And likewise, the government sector and policy is also aligning around this effort. Lots of momentum building with city and state policies leading the way. We have ASHRAE and IECC are both anticipating net zero performance to be required in their next set of standards. California, Washington, DC. Here in BC, we have a step code for buildings where the highest step is zero energy ready, and that's for all new construction by 2032. So really great momentum supporting the transition. And unlike the automotive sector, the building sector hasn't focused on performance metrics historically, and buildings aren't often designed to be able to track performance and use. All of these Examples, step and stretch codes, zero emission policies, passive house standards, great example, and net zero certification pathways are shifting that. So we list a number of performance metrics here: total energy use intensity, GHG intensity, that are going to be much more important for the building sector to start to produce on a regular, consistent, and verified basis. And embodied carbon is included in that list as well, as being one of these emerging metrics that we're going to be paying closer attention to. So what is, how do we measure embodied carbon? Well, it's life cycle assessment, LCA, which is a framework for measuring the impact of a building or a building product across its entire life span. And the goal of LCA is not only to create data, but also to facilitate decision-making from a designer standpoint, but in also specifying materials. And so EPD, or environmental product declarations, are the sort of emerging nutrition label for building environmental products. And that tells us how much embodied carbon is tied up in a unit volume of a building material. So we can compare between similar types of products. And EPDs are proposed for use in procurement, as well as supported by national databases and international databases. And so I just wanted to sort of summarize the landscape as we see it. 2020 was a huge year for net zero goal setting. And this is an example of a number of companies that have set goals that year or in the year that followed. Some of these have more teeth than others. And the reality is that many companies have no idea how they're going to hit their targets. So to date, we know that 50 countries and 21% of the world's largest corporations have net zero targets in place. And that net zero is really based on a planetary perspective. It describes a scenario where the atmosphere is on balance and no longer building up GHGs. So for companies, net zero is a commitment to A, peaking emissions, B, driving down emissions, absolute emissions reductions, and then C, neutralizing anything they can't drive down by investing in growing natural carbon sinks or carbon removal. So quick wins to help companies like those listed on the slide to get on their net zero pathways are solutions that focus on efficiency, waste, and rapid emissions reductions. And that's where companies like Nexi come in, and really on all of us in the built environment to help them get there. So with that, I'll pass it back to Laurenz to talk about how offsite construction and rapid assembly is a great scale solutions we need today.
So construction sector inertia, let's examine a few building materials as a case study for the construction industry as a whole. So as an example, drywall. It's an example of something that was very labor intensive, and we did as much as we could with lath and plaster for centuries. Then drywall was introduced to the market. It can be mass manufactured. It's labor reducing. It is a fast product for walls. However, it really didn't take on much until the post-war construction of the 40s and 50s, several decades later. And now it's been a great material for the period. It was definitely an advancement over what came before it. It is essentially, it's a very similar product to what it was and has been for many years. There's new compounds to use with it. There's varying thicknesses and what, but it is still the same thing, and we still use it today. So there's an opportunity to improve process with new materials. So the industry itself, it favors the use of established specifications, so therefore established materials. The A&E industry is really risk averse in a lot of ways, and new materials are difficult to be accepted. Additionally, every building is a one of a kind. I myself have practiced for close to 25 years, and have never built the same building twice. And even if I did, it would be a completely different team of contractors that are building that. So there's really almost every building, there's some new learning that goes on. And of course, we all know that there's a lack of integration of building systems in the buildings themselves, and oftentimes we're not even designing for that. Generally, on a construction site, first trade to get in there gets the best location to run their system. All others that follow have to work around them. And for all of you that have been on a construction site, that fourth bullet, working, putting a car together in a muddy field it sounds fairly accurate. Definitely on a lot of the sites that I've been on. So, and design improvement is an iterative process, and you can't do that when you're always doing a one-off. And lastly, there's obviously a lack of accountability on performance. Again, those of you who have been are in the A&E industry have likely seen projects where deficiency lists are like small small novellas, and often take months and months to get through those. So let's look at a panelized solution for today's design challenges. First, let's talk about building envelope principles. There's the 4 Ds of water management: deflection, drying, drainage, and durability. These two diagrams really, are more akin to a residential project, but essentially the principles there are all the same, regardless of if it's a single-story residential building, or it's a multifamily, or it's a large commercial building. We always try to make sure that we take care of these components because they work. I think this is a great slide. It really points to the complexity of our building envelopes at this stage of the construction industry and the design industry. There's a lot of challenges with them. The thermal layer, where do you put that, and how do you make sure that it's continuous, especially when you have structural components that have to go through? Where does the air seal go? We have at least 2 layers of insulation here. Does it go in the inside, in the middle, on the outside? How do we deal with all the sealants and flashings, et cetera, and make sure that we can keep the water out? And then how do we take this assembly, and there's about at least 12 components before we even get to the brick veneer. How do you transition that to a punched window frame, or a curtain wall, or a window wall? And then how do all of these components interact dynamically in varying freeze-thaw and all hold together? Now, the upside to that is exactly this diagram. We now live in a digital age where in the A&E industry, we model everything in 3D. And in fact, these sort of 3-dimensional details have found their way directly into our contract documents. And we need them because when you are in the field doing this work, if you don't actually understand the 3-dimensionality of it, you'll never be able to get it right. And getting it right is the most important part of our building envelopes. So let's move on to some examples of conventional building envelope materials. I would argue that the ones on the far right, the curtain wall, window wall, or ornamental fiberglass, these theoretically could be whole building envelopes. Certainly there are lots of examples of curtain wall buildings that are completely wrapped. I guess the ornamental fiberglass, maybe that would be a really funky TELUS data center that doesn't really need any windows, and so could become the entire envelope. Now the 4 on the right hand side are really, they're components of a building envelope, but they're not the whole envelope. And that's part of the problem. They just deal with a component of that. So let's move on and let's look at what Nexi has developed. I'm going to admit these photos are a little bit old, 3 years. That's a long time in Nexi time. The photo on the far left, you're looking at two components, two panels that are attached together with two different finishes on it. The reality is with casting into form liners, we're able to cast a number of different textures into our panels. And by applying paint or various colors of paint, we're able to achieve different looks and textures on that surface. Panel in the middle is showing the backside, and the darker color is actually the color of the Nexi. We would generally send it to the site with a primer coat on it so that the finish coat could be installed on the site. And you'll notice these HSSs in the corners, called corner blocks. We have developed our connections further than this older image. However, it's really the same process. We bolt our panels together. We bolt them to the foundation. We bolt roof panels to wall panels. It is a fully, it's like a large mechanoset, for those of you who remember that. Image on the far right is a side view of our panel. The exterior side is on the left. So you see that exterior finished panel. And directly behind that, you can see grooves horizontally and vertically. Those are effectively our rain screen just behind the finish. Then we have the EPS, and then you see the interior skin, and you also see a thickened edge. That thickened edge is reinforced in this image with rebar. Sometimes we actually have steel members in when we need additional strength. But that thickened edge runs all the way around the panel. It runs around the door frames and window frames or any openings to provide the additional strength to that panel. So what this does, it eliminates the need for traditional wood framing, steel framing, insulation drywall, exterior vapor barriers, and exterior finishes. It's all in one panel, all produced in a indoor manufacturing facility to tight standards, wrapped, shipped to site, unwrapped, lifted into place, bolted to the building. Next slide. This just gives you a little bit more detail on the actual sandwich of that panel. Again, on the left side, the exterior face, all the things I described to you, the face, the rain screen, the Type 2 EPS core. We add a layer of FS, which is our version of Nexi for fire and sound. Half-inch of FS provides a half-hour fire rating, and then we have another layer of the ST on the inside. The ST, because that stands for structural, so we have a structural skin on the outside, we have a structural skin on the inside. That structural skin ties to the thickened edge and oftentimes all the way around to the exterior face as well. With that 8.5 inches of EPS, Type 2, we get our 34, and our maximum panel size is approximately 12 feet wide by 35 feet in height or length. And our panels can go horizontal or vertical. Let's head to the next slide. So what are the advantages of a Nexi panel or a panelized solution? I love this first one, material supply chain predictability. That was probably accurate when it was initially put into this slide deck. As we all know, that is not the case today. However, in the future, as Nexi grows and locks down and has consistency in the types of panels that we're producing, we'll be able to buy in bulk well in advance of projects arriving through the door, so that we have product on hand for our panels. The rapid assembly is obviously key here. Typically, we basically say a panel can be installed in about half an hour top, maximum time. And of course, doing that gets us to, closing the building in as quickly as possible, which is always a desired effect. There's a higher potential for systems integration, and we do that quite often. Any penetrations through our panels, we like to coordinate all of those in advance. I talked about manufacturing in a facility. In fact, our Moose Jaw facility is ISO, and our Moose Jaw facility will be soon. So a high degree of quality control and quality assurance. There's definitely cost savings available when there is a repetition of panel. Then it gets easier for us. One drawing that can make dozens of panels is obviously makes life easier. There's significantly less construction waste in our process than conventional, and the repetition of the process gives us an opportunity to learn and to innovate and make it better. The challenges, it does require tight tolerances. We can hit those tight tolerances in the plant. What we've found is sometimes conventional construction, and I say sometimes with a little bit of tongue in cheek, because often the conventional industry cannot achieve the tolerances that are even normal. We do require experienced crews to do the assembly, but we have taught several crews already, and it is actually not that difficult. And then on the unfamiliarity side, not necessarily the crews, I would say more so designers. So we spend a lot of time educating the AED industry on what we have to offer and why and what and how, so that they feel more comfortable with using it. So here's an example of some projects that Nexi has been involved with. There are some misconceptions or maybe preconceptions about panelized construction, that it is perhaps limiting in design potential. The top left, middle, and top right, all three projects came to us already designed conventionally, and we effectively were able to match what was designed and provide exactly that to the client. So not really challenged. So top far left, Louisiana chicken, Popeye's chicken. That's in Abbotsford. On the far right, also in Abbotsford, is a Starbucks that's been open since January of this year. Later on, Zosia will show you a video of that. In the middle is the Marriott Courtyard in Nanaimo that is currently under construction. On the bottom left, a industrial building in Allendale over on the Vancouver Island. And on the bottom right, a house for, Zosia, help me with the name.
Paradise Valley.
Paradise Valley, California. We were working with a developer who was looking to produce homes that could be built in Paradise Valley, because right now you cannot build a conventional house there because you cannot get insurance, because they've had fires twice now there. So we designed and produced all the drawings for a house that could actually meet the fire code and get insurance in that area. Unfortunately, that project has been put on hold. And with that, I'm going to pass you back to Zosia, who will essentially take us to the completion of the presentation.
Okay, great. We were going to take a quick look at the Starbucks building and share a video of how that came together. And, conventional CRU or commercial retail unit buildings tend to be high carbon buildings, typically made out of concrete or steel stud, high in both embodied and operational carbon, can take 4 to 6 months of on-site construction, where speed to market is a major driver, and generate a ton of waste along the way. So here's a video, I hope this works, of how our Starbucks came together. Okay, so that's a snapshot of how Nexi provided the walls and the roof for this Starbucks building. Panels arrived exterior finished, interior paint ready, 6 days to assemble that envelope. And we did a life cycle assessment to compare the panels produced for Starbucks versus concrete block, steel stud, and CLT, equivalent baseline design. And we saw a 20% reduction compared to steel stud or concrete block design, so roughly on par with CLT for these panels. They were an earlier panel than what we're producing today, which is showing even better embodied carbon reduction compared to baseline. 43% reduction in GHG from operation in this building, and that really comes, and that's driven by 55% reduction in heating demand. And that really comes from the highly insulated airtight envelope. We did a blower door test on the building, 40% improved air tightness compared to conventional build, and near zero on-site construction waste, just bringing the materials that we wrap our panel in to protect them in transportation, and that all comes back to the plant with us for recycling or reuse. In this project, we saved 13,500 pounds from landfill, and that was an estimate compared to what Starbucks might conventionally produce for a building of this size. And free of redless materials, so healthy materials going into our panels as well with reduced off-gassing. And, this is available on our website. It's a snapshot of our green metrics to date, kind of averaged across our projects. We're committed to tracking our performance, the performance of our panels and the buildings we produce for every project, and working with third-party verification for many metrics, as many as possible across the board. Embodied carbon, water, looking at R values and air tightness, energy savings, and healthy materials. So what's next for Nexi? We're looking at, this is an example of an integrated technology partnership that we've got with a number of kind of key marquee companies, including Siemens, Trane, and Honeywell, where Nexi provides a very high-performing building envelope, and we work with leading technology companies to help us with the extremely high-efficient systems, building controls, smart appliances, integrated solar PV, etc. So essentially, it's a kit of parts that's net zero ready, and this is something we've got actively under development, hoping to deliver our first building of this kind by the end of the year. And then also, just to highlight that most of our presentation has been focused on our environmental impacts. At Nexi, we're very much thinking about the triple bottom line, thinking about a purpose-driven company that wants to drive low carbon growth, but that also means creating jobs. It means equity and inclusion. It means we're focused on our communities and transforming living standards and having a product that's available to all, and really focused on that community resilience piece as well. So bringing disaster resilient, durable solutions to communities that are the most impacted by climate and natural disasters. This is our 8 long-term impacts that our whole sustainability strategy anchors on, and we're going to be sharing our public goals that tie to these long-term impacts in the next few months here. So I'll just end with a slide, which is a question we ask ourselves at Nexi every day. Why do we exist? Why are we here if it's not to make our planet better?